Okay, Erickson, I think we are live. Let's take it away.
Okay. Thank you, Marek, for the setting up. So, hi everyone. Good morning, afternoon, evening, depending on where you are. So, this is supposedly the last part of what I volunteered to talk about, which is introduction to algebraic stuff. So, just to recall, I put the word algebraic stuff because the word stuff is intentionally vague, but I hope it has given you some interesting perspective of how we do quantum mechanics. But today's one is going to be a little bit technical, but I try to keep it within 30 slides or less. So hopefully I managed to do something that is sort of condensed. Feel free to stop me whenever you need. But otherwise, just beware that today's one, I'll try to go through a little bit slowly, motivate a little bit about the physics. And I will also mention what I will not do today for various reasons, including the fact that I'm not qualified to talk about some topics. Okay, so today is going to be somewhat interesting for some people who has not seen this. It's going to be about the modular theory, Tomita-Takesaki modular theory. It is a very deep mathematical subfield of operator algebras. And this, you might have heard fancy stuff from people in quantum gravity. Okay. And the way I would motivate this, as you can see from a little bit of a spoiler in the outline, I will motivate this mostly using thermodynamics because this is really the only angle I know how to see this. So first of all, let's recap what we did. So 1 month ago, I did part 1, which is Introduction to Operator Algebraic Framework in Quantum Physics. Basically, how does the C-star algebra's GNS theorem algebraically reformulate quantum mechanics? So it's, in a way, you can think of it like a Heisenberg representation of everything you do. Although you can also, there is also an operator algebraic way of making sense of Schrodinger picture. And then part 2, we talk about introduction to von Neumann algebras, like what it means for two observers to be like operator algebraically commute with one another. And then there is a technical classification of von Neumann factors, which matters depending on what kind of system you have, whether the system is in thermodynamic limits or not. But today I'm going to talk about something that is, I think, both very technical, but also very exciting. And this is part 3 about Tomita-Takesaki modular theory. And here I need to put the 3 references right from the very beginning, because so it's 1 review paper by Ed Witten and 2 papers by Jonathan Sorte. And the reason I'm putting this up is that you might be able to find mathematical papers on these subjects, but these 3 are, first of all, physics, but second is all high energy physics. So if you are not working on high energy physics, so for example, I'm not sure if in the audience there's anyone who does like non-local games, Bell non-locality. This might be one of those things that you find it very hard to find a good review about. But at the same time, in the quantum gravity community, this has been around for a while. Okay, now I'm not going to be able to cover some of these nice topics. For example, the concrete constructions of von Neumann factors. This is done in Ed Witten's papers, but really I don't have time to go through this. But it's very concrete. And then there's also non-local game stuff that I mentioned. And for example, there's one paper very recently, actually, it's talking about synchronous correlations and Tomita-Takesaki modular theory, but I'm not qualified to talk about this. And the last one is the applications to quantum gravity, which the most recent paper in September was about the argument that the generalized black hole entropy is basically the von Neumann entropy in the sense of the von Neumann algebras. Okay, and there's also many other topics that I'm not possibly aware of, because actually Tomita-Takesaki modular theory is kind of like a structural theory that gives rise to many way to understand the von Neumann algebras. Okay, so let me start by something that is kind of cute. So I'm going to do a little bit of quantum thermodynamics. Okay, so first of all, I hope everyone is familiar with this notion of Gibbs state, which is just the exponential of minus beta Hamiltonian divided by the partition function. And you can rewrite it in several ways. And you can also think of this as just a generalization from the statistical mechanics of thermal states. But then what you realize is that you can reverse the logic. Okay, so if you take a max rank density operators, I mean density operator that is completely spanned, so there's no 0 diagonals, for example, then you can, because it is max rank, you can always write it as exponentials of minus k, where k is some operator. And this operator, because it has no 0 eigenvalue, you can always write it as just a simple minus log of rho. Okay, and we will call this the modular Hamiltonian as a spoiler. But even for people who do not know modular Hamiltonian, they will call this a modular Hamiltonian because of the technical reasons. But the reason why you can write this is that you realize that equation 1 has nothing to do with thermodynamics. Okay, But then by writing in this form, basically a lot of tricks from thermodynamics, you can use it here. So for example, if you can try to compute the free energy, now you can start asking in quantum information, what does free energy in the sense of modular Hamiltonian means? Okay. But of course, you see that this construction only works if the Hamiltonian is trace class. That means you can take the trace. So in infinite dimensional quantum systems, you cannot actually do this, especially let's say you do quantum field theory or you take a thermodynamic limit of something. Okay. Now, so I just said that it really only works if the thermal states are always density operators. That means in the sense that the 1 over z there is actually a number. Okay. So an example where this doesn't work, of course, is thermodynamic systems at infinite volume, the thermodynamic limit of spin change, for example. Well, the partition function is just divergent. Or you can talk about local subregions of quantum field theory. So you might have recalled that last session, I talked about certain situations where you might not have density operators at all in your algebras. In this case, if you don't have density matrix, there's nothing to talk about Gibbs states, right? So the key point is that all the intuition you have from Gibbs states, being able to write it as something about partition functions really only makes sense if density operators are available to you. And also, you realize that standard quantum information stuff, like the von Neumann entropy, relative entropy, mutual information that you know in the standard formalism, always requires one or at least two density matrices. Or, right? Even mutual information, at the very least, you need rho A and rho B to be density matrices, even if rho AB is a pure state on some global algebras, right? So all of this really depend on the fact that whether you have density operators available to you. And you can also see that why in finite dimensions, none of this matters, because you always have it, okay? And I encourage you to look at Ed Witten's lecture notes. So actually, this is pretty good because I'm 7 slides already. But I hope this example makes clear that, well, if you think that you always work in finite dimensions, then everything is all okay. But whenever you start thinking about thermodynamic limits, continuum limits, and many other cases beyond finite dimensional arguments, then some of these questions may start to become important. Okay, now I'm going to claim that one of the ways to think about Tomita-Takesaki modular theory, which is not how historically it was solved, is that one, it is possible to formulate thermal states without Gibbs formula. And this has nothing to do with Tomita-Takesaki modular theory. And second, if you do have Tomita-Takesaki modular theory, you are actually able to compute relative entropy even if you don't have density matrices. And unfortunately, how you do this explicitly, I will not show it today. It's again in the Edward Witten's lecture notes. But the key is that there is this operator. Remember, the k equals to minus log of some operator is the modular Hamiltonian, right? The key is that you need to make sure that there exists an operator called the modular operator whose minus log is the modular Hamiltonian. So the problem is that you want to make sure that these operators exist. Otherwise, you cannot define the modular Hamiltonian. And the whole properties of the modular Hamiltonian and how this single operator defines the entire way of making sense of all these complications is actually the whole subject of Tomita-Takesaki modular theory. So it might not look like it's about thermodynamics, but you can completely think of this in terms of thermodynamics.
So Erickson, you're taking the log of the density matrix, you get K, and then you take another log, and then you get
So in finite dimensions, what I was claiming is that any density matrices that is max rank, you can always write it as exponential of minus K, where the delta here is the rho, right?
The delta is the rho. Okay.
Yes, but remember, I just told you that in some cases you don't have the density operator.
Yeah.
But I'm going to claim that there exists another operator called the modular operator, so that in finite dimensions, it's gonna be an object that is constructed out of density operators.
So when a density operator exists, it's equal to this delta?
No. The point is that even if the density operators do not exist, delta can always be proven to exist under some conditions.
And if delta exists, then they are the same?
No. My point is that you may not have density operators at all, and delta still makes sense. And whenever density operators exist, delta will just be a simple formula in terms of density operators.
Okay, related. Okay, okay, thank
Yes,
you.
they are related, but they are not the same thing. And depending on whether your system is a single particle system, which is the example I gave, or a bipartite system, delta is not going to be just the density operator, but it's
Yeah.
going to be made of density operators whenever they make sense. And I will show you why.
Okay, okay, thank you.
Okay. And this is a very beautiful result because the thing is you can have no density operators at all, but you can prove that with a good conditions, delta always exists and exists in the functional analytic sense. That means you actually it's not something that physics sketchily do, but you can always prove that it is a proper self-adjoint operator with a proper dense domain and whatnot. Okay, now I'm going to run through basics of Tomita-Takesaki modular theory, and it might be a bit counterintuitive because the main selling point is for infinite dimensions, but I'm going to use finite dimensional stuff to actually make this argument. Okay, so first, let me tell you how do you start making sense of modular theory. First, you need an input. The first input you need is a cyclic and separating vector for von Neumann algebra. So this is something that I mentioned last session. Well, let me recall the definition. A definition of cyclic and separating vector is the following. I give you a von Neumann algebra, which is a subalgebra of bounded operators acting on some Hilbert space. Now, a state in that Hilbert space is said to be cyclic for this algebra if you can essentially generate every vector by applying some operator there. So the technical term is the algebra multiplied by the vector is dense in the Hilbert space. Okay, and then it is separating for this algebra if the only element in the algebra that can annihilate the state is the zero operator. Okay, so I gave an intuition from quantum field theory last time is that if you know a little bit of Riesz-Leiter theorem, right, then basically the idea is that any local algebra acting on the vacuum is actually cyclic. And what that means is that the annihilation operator, the AK that we always write like a harmonic oscillator, is not actually part of the algebra because it is not localized. So that means there's no local annihilation operators in quantum field theory. Localized in space-time, I mean. But basically the intuition is that cyclic means you can generate every vector just by acting with some operator inside the algebra, and separating means the only annihilation operator in the algebra is the zero operator. Okay. Now you can also prove this interesting thing that shows that if a state is cyclic for one algebra, then it has to be separating for the commutant. So if you think of Alice and Bob being separated in a space-like sense, so their operators always commute, then if a state is jointly for them is cyclic for Alice, then it has to be separating for Bob if this state is commonly shared by both of them. And the way to prove it is actually very straightforward. And I will leave this proof here. But one direction is, for example, you say that there is an operator that annihilates the vector. Then since they commute, you can just swap A and B, and you realize that then B must essentially annihilate all states in the Hilbert space because A, you can run through all A's in the algebra of Alice to get every possible state. And that, but the only operator that can annihilate every single state in your Hilbert space is the zero operator. Okay, it's a very elementary trick. Of course, I put a quotation mark all states because if H is infinite dimensional, you just need to make sure that B annihilates a dense subset of H, and then you are done. And then the other direction, you just swap B and A. Okay. So the point is that if you take this sentence and read it in another way, if a state is cyclic and separating for UA, then it also has to be cyclic and separating for UB, right? So it has to be cyclic and separating for both if it is cyclic and separating for one of them. And let's try some examples. Okay, so the thing that we know is a von Neumann algebra is the local algebras of bounded operators on Alice and tensor identity with Bob, and same thing for Bob. So basically they can do every bounded operations on their own regions and nothing on the other side. And clearly, I hope it's obvious that the algebras commute, well, because of the tensor identity, right? And also the only common element for both of them is the joint identity of both up to proportionality constant, right? And remember, I mentioned that to start doing modular theory, you need a cyclic and separating vector, okay? And in finite dimensions, it's actually very clear-cut what kind of vector this is. You can actually prove that if Hilbert space A has dimension dA and Hilbert space has dimension dB, then in finite dimensions, a vector is cyclic and separating if and only if, one, they have the same dimensions, and they are basically a state that has a max Smith rank. Okay, so that means if you do a Smith decomposition of the vector state, then there is no zero coefficients. And you can actually understand this very easily, right? Because if one of them has zero, then that means there is some operators that acts on that subspace and it annihilates the state, even though the operator is not zero, and so it cannot be done. So basically, we call such a state max rank. Or another way to think about it is that if you partial trace A or B, the density matrix will be max rank. So I hope this makes you recall the first example in the very first slide, right? So you can always think of it as has maximum Smith rank, or the reduced state has maximum rank in a matrix sense. Okay. And once you have this, the goal is to construct the modular Hamiltonian based on basic operators in the modular theory. And this is what I'm going to go through. And in modular theory, there are several operators. Actually, there's 3 of them that is important. First one is a Tomita operator. Is an anti-linear operator associated with an algebra such that it sends an operator to its Hermitian conjugate. Okay, it might sound like a weird thing, but it does this, and it has some nice property that I'll leave it to you as an exercise. But in particular, you realize that this operator is affiliated to an algebra, right? So if you look at the second properties, right? If S prime is the Tomita operator for the other person, which is the Bob, right? Which is the commutant of Alice, then you can actually show that the Tomita operator of one person is actually the Hermitian conjugate of the other guy. Okay. And then S, because you see, the first property says that S is invertible because S squared is identity, right? So it is its own inverse, which means that you can do polar decomposition, and this is going to work even in infinite dimensions. And polar decompositions of anti-linear operator is going to give you a J, which is anti-unitary, anti because of the anti-linearity, and delta of 1/2, which is by convention, is Hermitian and positive. So you can think of this like a matrix version of writing complex number as R times e to the power 5 theta, right? That's the definition of polar decomposition. And that delta there is the definition of a modular operator. And you can define this to be basically S dagger S, right? Because you can just take equation 7, Hermitian conjugate, and multiply them. So the modular operator is defined by this operator, and you can check some properties. For example, J square is identity, S square is identity, and therefore J, which is what we call modular conjugation, sends delta of half the square root of delta to us 1 over square root of delta. And this peculiar property might not be obvious why it is important, but J is called modular conjugation in the sense that it is something that, roughly speaking, behaves like an imaginary number. So J is something that basically it does a reflection around the origin, but this is far from obvious, and I will leave it to you to read up more if you're interested. But J is not the most important one for us right now. But again, I want to also say again that these operators are defined with respect to a vector omega, and also defined with respect to an algebra. So if you want to find what happens to the commutant, you have to check the commutant, and in this case, you can verify that for the commutant, the J is the same, but the modular operator is actually the inverse of the other person. Okay, and again, I will leave it to you as an exercise. Yeah. Yes.
So when you explained it on the previous slide, you were using our Hermitian conjugation. Can you say in what way this encodes the state? So S is labeled by omega if I will have some other state psi.
Yeah, so the point is that it depends on the state, because it is not true in general, I think, that S times A is A dagger. You have to apply it on a state, and then the state sends it to A dagger. So if you remove the state from equation 6, I think this statement is false.
So in general, we wouldn't be able to construct such operators, or
I think it is just general. I mean, in finite dimensions, probably you can make sense of this, but I think this is an operator that is affiliated to the state. That's why if you change the state, you're going to get different answers.
Yeah. Because I'm asking just to not get lost, because
yes,
on the next slide you're saying this equation number 6 is already giving us this modular delta, yeah?
equation
So equation
no.
number 6 looks quite simple, but somehow it encodes some information about the state directly, right? Because then
Yes.
after the polar decomposition, yeah, you're saying it here. This is the modular operator, yeah?
Yeah, the complication part is in the action of S. So the thing is that I think, morally speaking, if you change omega, you're gonna get a different S. And I think this might be easier if I give you an example later where the basis expressions of so the action of S on a particular basis will depend on coefficients that depends on the state. So basically, you know how in linear algebra to check the action of an operator, you just apply it on a basis and check what happens, right? And for S, you realize, for S and delta, you realize that in a particular basis, the matrix elements are actually dependent on the coefficients of omega.
Okay, okay, I understand. And then can you say the definition, because maybe you were just shortening it, but can you repeat the S I have to define for those cyclic vectors?
Yes.
Yeah.
So take a cyclic operator, fix an algebra, a von Neumann algebra, and the Tomita operator is an anti-linear operator affiliated to this algebra and the state, so that the action acting on this state is equivalent to taking the Hermitian conjugate from that algebra and apply to the state.
Yeah.
And then S being invertible means that you can do polar decomposition, and then it will decompose into J and the square root of delta. This is just linear algebra. And then the modular operator, just from 6 and 7, you can just combine them to get a modular operator. So at this point, it is a very mathematical object. But the important thing is that these operators makes no sense without reference to one, the algebra and the state. Okay. Now, one important property you can check is that if you take some functions, well, reasonably good functions, I mean, not crazy ones, then J times the functions of the modular operator in the sense of spectral decomposition will actually give you the complex conjugate of that function applied to the inverse. And in particular, the ones that is most relevant to us is F is just a complex imaginary exponent of itself. Then J actually maps the delta IS to itself. Okay. And consequently, only when delta is exponentiated with an imaginary number that actually J commutes with it. Okay. Now, this might not look very enlightening to you, but if you think about it, delta is like exponent of minus K, right? The modular Hamiltonian, right? Morally speaking. So you realize that this delta is like a unitary time evolution. So this is telling you that, morally speaking, equation 10 is just saying that the modular conjugation maps the unitary time evolution generated by the modular Hamiltonian to itself. Okay, and we will see what happens. This is a very important result. Okay, so let's try it on finite dimensional examples. Let me see. Okay, my time is hopefully I'm gonna make it. So in the finite dimensional example, let's say you want to take you want to find S omega, right? So remember, in finite dimensions, we have to think of local algebras of Alice as a tensor identity, right? And if you pick some basis vector and element, so you try it on elementary matrices. So elementary matrix is like the matrix with all zeros except at one entry. And if you try to run this example, you realize that equation 11 is true. So what happens is that if you take a basis element I and j in the joint Hilbert space, and there's a complex number in front, anti-linearity means you bring complex conjugate out, and then you can just reshuffle and show that S acting on a basis element actually flips the index of the vector, and also there is a coefficient in front that depends on omega. So this is what I meant by this operator is completely slave by the cyclic and separating vector, for example, right? So it makes no sense to talk about S as a genuine operator independent of the basis. No, I mean, it is independent of the basis, but it cannot be independent of the vector. Okay, and then now you can try to do what happens to J and delta, because it is just linear algebra at this point, and you realize that delta is actually applied to J and I. J and I is an eigenvector of this with a coefficient that is the ratio of the modulus. So it's a as I promised, is a Hermitian and positive semi-definite operator. Okay, and the polar decomposition guarantees that J is a modular conjugation. Literally, it flips the indices of Alice and Bob's basis vectors. Okay, and the proof, I hope you will do the exercise because this is very instructive and you can find it in Witten's one. It's a very cool example. Okay, and now let's try something more interesting. And if you give me a joint pure state, which is cyclic and separating for both Alice and Bob, and now you define the reduced density matrix of each, now you can check that in finite dimensional case, the modular operator is actually the reduced state of A times the reduced density inverse of B. And you can see why I need cyclic and separating vector. Because if I'm not cyclic and separating, I'm not max rank, then rho B inverse doesn't exist. Okay, so I need this to be true, but I hope it's also interesting that if you, I don't know if it is obvious to you at this point, but if you take equation 14 and you take the log and you take expectation value with respect to rho AB, you are gonna get relative entropy, and that inverse in the rho B is basically the, relative entropy is trace of rho log rho minus log rho sigma. That's the thing. Okay. Please try it. I mean, that's very interesting. Okay, and now I'm going to talk about Tomita's theorem. This is the most important result for today, and it's a bit mouthful, but the implications is a bit easier to understand. So if I give you an algebra and it's commutant, so think of Alice and Bob, and I give you a cyclic separating vector for both algebras, then the Tomita's theorem, which makes him famous, was that the modular evolution acting on the algebra is itself. So you see, equation 15 is just the unitary dagger acting on operator times, so the Heisenberg time evolution with respect to the modular Hamiltonian is itself. Okay, and the modular conjugation sends one algebra to the other. So this is a very big result. Of course, if you are a physicist, maybe it's not obvious why this is important, but basically, first of all, because of the modular time evolution, it actually defines what we call a modular automorphism group. And the way to make sense of this is, again, if you define the modular Hamiltonian as minus log of this modular operator, then the exponent of IS is just a unitary operator, and you realize that you can rewrite the first part of equation 15 as the statement that there is a unitary time evolution generated by the modular Hamiltonian on all the operators of the algebra. Okay, maybe the minus sign, I put it wrongly. But I hope this part is at least superficially clear that we are talking about time evolution of operators. And then in finite dimensions, you realize that this is actually very clear. So for example, to show that the algebra is invariant under the modular conjugation, under the modular evolution, you can just apply the modular automorphism on Alice's operator, and you realize that the rho B inverse cancels each other out, but then the rho A evolves via the time evolution, and you realize that rho is e to the power of minus k, so it's basically time evolution in the modular time direction. Okay, and you can also check that using the basis, working in the computational basis, any Alice's operator acting on the J is going to get sent to the dagger, but it's now on Bob's side. And then you can swap the role of UN and UV. So please try this. I mean, this is one of the things that I realized that in the Tomita theory, in finite dimensions, if you work out the details, it's actually very instructive. Okay, and now all this technical stuff really only matters, I think, if you can see why I keep talking about modular time evolution. And let's try this, and I hope I can make it in time. Okay, so I'm gonna go back to quantum thermodynamics and look at Gibbs state again. Okay, so in standard quantum mechanics, if you have a Hamiltonian, you can do Heisenberg time evolution, right? It's just e to the power of IHT times operator times the conjugate, right? And then you can compute the 2-point functions of the two operators, right? So for example, take two operators A and B, and you compute the 2-point function where B is at time 0, but A is at another time t. And you compute it with respect to a thermal state. So let me define F as the thermal correlation functions between A and B at 2 different times. And you realize that by shuffling through, this is purely a function of imaginary time t, I times t. Okay, equation 18 is just trivial. But what's not so obvious is that you can analytically continue this function from just imaginary line to the entire to the complex plane. And this function is going to be holomorphic or analytic only on the strip where the z is the real part between 0 and the inverse temperature beta. So that means on this strip you can the thing is differentiable. Okay, if of course the Hamiltonian is bounded from below. Okay, this is just the Kubo-Martin-Swinger or KMS condition. And this is just a mathematical trick, like you just do analytic continuation. You can always do this. And then you can check that. So this strip has boundary between real part of z being 0 and real part of beta, right? So if you just compute those, one of the boundary value is the original thermal 2-point function. But then if you compute at the other boundary value, it's actually swapping the role, the B and AT swap positions. And what I want to emphasize here is that you see, if I write it as equation 20 and 21, I no longer have density operators here. I'm just saying that if you have a thermal state, its thermal expectation value will look like this. Okay, and it turns out that it is true. That means even if you don't have Gibbs state, this can be made into the definition of a thermal state. And this is the statement of KMS condition that you might have heard in in quantum thermodynamics, which is that if I give you a von Neumann algebra, some Hilbert space, and if H is some self-adjoint operator, okay, which you might think as an Hamiltonian, but it doesn't have to be even. Like a state is KMS with respect to some H at inverse temperature beta. If 1, it generates the symmetry of the state. So that means this state is time translation invariant with respect to this H. H generates also the symmetry of the algebra. That means if you take element of the algebra, it doesn't bring it outside the algebra. And the last point is that that function I defined earlier, the 2-point function with respect to this state, can be analytically continued to that strip with the property that if you check the boundary values, it's going to swap. So this property formalizes everything you see in Gibbs state in finite dimensions, except that you don't need density operators to make sense of this. Okay. So this result is 70 years old. But the point, to summarize, is that KMS condition just says that thermality can really completely recast as an analytic properties of 2-point functions. It doesn't have anything to do with density matrices anymore. Okay. And since in physics, oftentimes we care about correlation functions anyway, so who cares, right? And now the question is, if I give you an algebra and a state, does that H exist, right? Because I need to give you the H to construct a KMS condition, and is the Hamiltonian unique? And the answer is that it's gonna work if the state is cyclic and separating. So you can actually check that the modular operator times is power to the exponent of is actually satisfies condition 1, which is it generates the symmetry of the state if and only if the state is cyclic and separating. So you can just try by direct computation that it is true. And therefore, you can now take the minus log and now define the modular Hamiltonian, and you now say that K generates a symmetry for omega. So now you see that in the KMS condition, that H is going to be replaced by the modular Hamiltonian. And now the question is, how about condition 2, which is actually the hardest? You want to show that H is a symmetry for the algebra. But Tomita theorem gives you this for free. It tells you that this delta to the power of is, the modular time evolution, maps the algebra to itself. But the proof is highly non-trivial, but I invite you to look at this paper. And the last one is all we need to do this, which is that the theorem is called the modular KMS condition, which is to show that now if I have a cyclic and separating vector, I have the local algebra, then the 2-point functions in the algebra is going to look thermal with respect to this state if you use the modular flow generated by K. That means if you take the H to be the modular Hamiltonian and omega is a cyclic and separating vector, then to a local observer with algebra A, this state actually looks thermal. Okay, I hope this is kind of surprising. And the reason is because you can actually check that the 2-point functions is going to satisfy the KMS condition. So I think I should pause for like 5 seconds to let you breathe in this beautiful result. Okay, I'm gonna say it again. I give you a cyclic and separating vector for both algebras, and the claim is that with respect to the modular Hamiltonian, local observers think this state is thermal. Okay, and I can always do this for any cyclic and separating vector.
And local observers think that, yeah?
Yeah. I mean, if you take a global observers, I mean, the result is trivial. But anyway, so what this means is that basically, if Tomita's theorem actually holds for the system you're considering, then it basically gives you a thermal arrow of time. It tells you in what time direction your state is actually going to look thermal. And the reason is because, remember, Hamiltonian generates time translation, right? Which means that modular Hamiltonian generates modular time translation, but this is exactly the time direction in which a state looks like a Gibbs state. And a first remark I should mention here, especially for people in quantum field theory, is that you might have seen the imaginary time version of this. So this is like sometimes people talk about statistical mechanics being kind of like a periodic in imaginary time. You do weak rotation, this kind of stuff. You can rewrite it in that way, but it doesn't really matter. Okay, let me give you 2 examples where this example is very explicit. So first, let's consider global thermal state. So Alice and Bob has a cyclic vector, which is basically just the vectorization of their own thermal state. So remember, if I give you a thermal state, I can vectorize it to get a thermal 2-mode squeeze state, which is equation 26. And you can verify that partial trace of A and B is going to give you a thermal state with the temperature beta. Now, omega is clearly cyclic and separating because a thermal state has max rank, right? So none of the exponent of minus beta E is 0. So if you run through the modular operator, you realize that equation 27 is nothing but unitary time evolution generated by Hamiltonian of Alice, and therefore the omega, which is the joint state of Alice and joint pure state of Alice and Bob, is going to look thermal for Alice with Hamiltonian that is basically in the eigenbasis of whatever Alice is doing. Now, this might look trivial to you, but let me show you that this is not so trivial, because equation 26, I give you a thermal field double state where A and B might not even be in the same computational basis. So Alice could be in the plus minus basis and Bob might be in the 0, 1 basis. But this is telling you that if you take this state and construct the modular Hamiltonian, then evolution with respect to the modular Hamiltonian is telling you that Alice is going to look this state is going to look thermal if Alice's Hamiltonian were equation 28. So that means if Alice picks the right quantum system, this is going to look like a thermal state. Now, the most interesting of all, that maybe some of you are not familiar with this, is that the Unruh effect, which is about accelerating observers sees the vacuum state of a quantum field theory to be a thermal state. And I hope this is not so difficult anymore. The reason is because take a cyclic and separating vector, which is by Riesz-Leader theorem, the vacuum state of a quantum field theory is one of them. Well, you can now think of Alice as the right observer and Bob is on the left observer, which I give you as a diamond on the left and right. They both commute because they are causally space-like separated, right? And now you look for the same thing. So you look for the modular Hamiltonian, and then you look for the modular conjugation. And it turns out that if you run a quantum field theory computation, you can actually find in this simple case that the modular Hamiltonian is just 2 pi of the spatial integral of x times the stress energy density. This might not mean anything to you right now, but you can actually check from a quantum field theory textbook that equation 30 is nothing but the Lorentz boost generator along the x-axis. That means the operator 30, the integral curves of this operator, differential operator, is actually along a parabola along a hyperbola associated to a constantly accelerating observer, which means that the modular theory just tells you that if you are an accelerating observer, the ground state of a quantum field theory is just going to look thermal for exactly the same reason as the previous example I gave you. So if your system has modular Hamiltonian K, which is the same thing as what an accelerating observer would think his time direction is, then even the vacuum state will look thermal. Okay, but if you now pick the modular Hamiltonian to be some inertial time, then it looks like a vacuum state. But anyway, that's the end. And I don't know if this sounds anticlimactic, but I really want to make sure that this examples is not so far-fetched in terms of thermodynamic language. And I'm just going to leave some of the references I use here, and then I think I'm done.
All right, thanks so much, Erickson. Maybe there's some questions.
So I don't know if this is related to what you presented, but I've always been very troubled, very puzzled by people kind of hand-wavily talking about vacuum fluctuations, where they say that the energy of the vacuum is non-zero, and so you have like particle antiparticle pairs just sort of getting created and annihilated, whatever. And to me, this is very confusing because if I mean, I only understand something simple like, say, a harmonic oscillator, right? And there, yes, the vacuum has non-zero energy, but then the energy is just some kind of additive constant. Even though the vacuum has energy, it doesn't have any non-zero overlap with any states with excitations in them. So what is this like? Why is there being energy somehow causing pair creation or like stuff?
So
yeah.
So first of all, I should let you know that your intuition is correct in the sense that those things are hand wavy. And if anyone tells you that you take a harmonic oscillator with a 0-point energy and just take infinitely many of them, and then it has an infinite ground state energy and stuff, just don't believe in those. Okay. The reason is because if you take any course in quantum field theory, you might have heard about this thing called normal ordering, where you just remove the 0-point energy because they are not unobservable. But the whole point is that this is where you see you have to be careful about constructing infinite dimensional stuff. You cannot just take infinitely many oscillators, you sum everything, and you realize that it has infinite 0-point energy, and then we are screwed, right? And this is basically the problem with how to take thermodynamic limit. And I think that part is wrong. And particle antiparticle creation, remember that particle antiparticle creation is something that only makes sense in the cartoon picture of Feynman diagrams for quantum electrodynamics, where you have electrons and positrons. So if I give you a free scalar theory or free electromagnetic theory, it cannot create and anti-create photons. Does it make sense? So for example, if I want to have a photon-photon scattering, which is how the beam sabers in Star Wars work, right? Photon-photon scattering is a nonlinear process, but Maxwell's free theory is linear, so it's never going to happen. And you realize that, of course, that's true. The reason is because photon-photon scattering only happens in quantum electrodynamics, which is a theory with light coupled to matter that induces photon-photon scattering. So the moral of the story is that whatever I just told you is about free master scalar theory. So there is no anti-particle particle creation stuff. Whenever people say something like this, either they don't know what they're doing, or they know it, and therefore the cartoon picture can always be made rigorous, and you always have to ask in what sense this is rigorous. But anti-particle and particle creation pair is usually a Feynman diagram interpretation, which you can make rigorous, but that's a separate story. So Unruh effect, roughly speaking, has nothing to do with this. So for example, you might ask, how can I see excitations for the constantly accelerating observer, even though it is in a vacuum, right? Well, the answer is not surprising, because how do you make sure that an accelerating observer can constantly accelerate at any point? Well, you need a rocket, because imagine if you don't have a rocket, once you accelerate, you start radiating stuff, and then it's going to deflect your trajectory somewhere else, right? So you cannot be in this constant acceleration unless you have a rocket keeping this. So the energy budget is accounted for, because basically such an observer has to have an external drive, like this little stuff. So
okay, yeah, thanks.
think maybe Tomasa had one question, but in the meantime, one question. When you do this analytical continuation, those f's arise out of state. Is there a converse characterization if I give you some analytic function on some strip? Can you check whether this is coming from a state or how? I could define the f with some values, right? I could start associating some numbers. And is there a way to say if I did it according to rules of quantum mechanics or so?
Okay, so to my knowledge, you see the input to get this direction, right, is that I give you an algebra and I also give a state associated to a Hilbert space affiliated to the algebras, right? So if you want to construct the other direction, I give you random f with the right analytic continuation property. You have to also check the other thing because, like, for example, the original KMS condition, you need to satisfy 3 things, right? So normally it is not natural to construct the other way around, but all this is saying is that any state that obeys this property has is basically a thermal state, right? So I think you might have to dig out a little bit, but what is true is that KMS state is more general than Gibbs state, because you see in finite dimensions, Gibbs states are only a state is only Gibbs if and only if it is KMS, but in infinite dimensions, Gibbs state doesn't exist, but KMS state, like for all practical purposes, always exists. But the point is that KMS state is a construction that depends on H and a particular cyclic and separating vector. And this is important because it tells you that if I have a state and a local observer, whether that bigger state looks thermal or not depends on the Hamiltonian that the local observer has access to. So a vacuum state to an inertial observer is going to look like a vacuum state, right? Because to him, the generator of time translation is the standard partial t, the time direction, the usual time direction. But to an accelerating observer, it points the other direction. That's why thermal arrow of time is not the same thing as inertial time. Like that's one way to think about it.
So, may I? So Erickson, the holomorphicity, how physical is that as a condition? I mean, it's a very strong mathematical statement.
I'm not sure about a very strong mathematical condition because
analyticity is super strong. Yeah, I mean, yeah, but it really tells you everything about the system from the boundary. So you're assuming that the boundary, if it was analyticity, but for holomorphicity, is how much does that restrict?
No, so this is a bit of a technical statement. So the thing is that all the analytic continuation guarantees is that you can extend this thing to a holomorphic strip, but the boundary itself is not holomorphic, right? Because it's only continuous.
Right.
So I'm telling, all it says is that this function can be extended to a strip where inside the strip is a holomorphic function. This is just a theorem from analytic continuation. But then the claim is that our 2-point functions live on the boundary of this particular strip and it's only continuous on the strip. So it's actually a very weak condition on if you view this from the strip, then the 2-point functions is not analytic, if you get what I mean. It's a boundary value of a holomorphic function.
Right, but at the same time, how would you establish by experiment that you have this holomorphicity for a particular physical system?
No, I mean in particular, I don't think in experiment what you measure is the holomorphicity, right? Because the thing is, you see, in experiment what you are going to measure is f at the value of it and f at the value of beta plus it. Mm-hmm. You are not measuring anything here. But the thing is, the technical definition of KMS condition that guarantees this result always true. Basically, condition 3 tells you that these 2-point functions make sense just automatically from the fact that there is an analytic continuation to this strip. So this inside the strip, we don't even have to talk about whether we can measure the strip at all. Like,
right. Okay.
So we are not measuring the strip.
But so now we're measuring on the boundary.
Yes,
and on the two boundaries.
Yes, as
And
far
you
as
have
we
to
are concerned,
and you have to measure for continuous t. So for every possible t, you'd have to know,
yes,
and you'd have to be able to demonstrate that that is continuous,
yes.
which you can't do from experiment.
Well, I mean, this is true for any real experiment, right? I mean, for example, if I give you
Yeah.
a quantum field theory in free space, our Large Hadron Collider is only 27 kilometers. So how do you know this is infinite? Yeah. Right? But the thing is,
Right.
I think the way I understand it is that in quantum, in our real life experiments, there are many things that we declare as infinity the moment we are in a macroscopic region, right? So for example, if you have a Bose-Einstein condensation, which is a macroscopic collapse to the ground state, well, in the mathematical thermodynamic limit computations, we'll declare that a Bose-Einstein condensation is when we have infinitely many bosons collapsing to the ground states. But of course, in reality, we only have 10 to the power 23 bosons, and that's finite, right? So I think, at least to my knowledge, we have to sort of try to bridge this between experiment and theory, in the sense that what is effectively infinity in theory would have been what we call a macroscopic number of whatever in the experiment. And same thing, right? If I say that to check that something is thermal, you have to check 2-point functions at every possible t for all real numbers, which we cannot verify. But for all practical purposes, we only measure like 100,000 experiments, and we should be content with that, right? And if you have good reasons to believe why the 100,001 experiment might break away from this, then it's the job of a theory and an experiment to actually figure out why we should expect this to happen. I think that's the way I think about it.
So in general, those measurements are not easy, no? Because even 22 is not a physical observable. This is more something that appears in Kubo formula and so on.
Yes.
So we were actually working on how to measure this kind of stuff in quantum simulators, and there are some nice papers in cold atoms. They call it Ramsey interferometry, where you kind of make a rotation generated by B and then make some data analysis, and then you get access to those expectation values, generating them as part of a sequence of measurements. So, but for this you do classical processing and you don't measure this directly. The reason for this is exactly this kind of holomorphicity, because ATB is not a real observable, because A and B are Hermitian. You take the Hermitian conjugate and you get this F of beta IT, right? So this together is not Hermitian, because you could view this as Hermitian conjugation between them if B and A are self-adjoint, yeah? So and on the other hand, those formulas have some magic properties, no? Because you can have also those retarded Green's functions, and then they generate the whole thing, and yeah. So, but Peter, your statement is that basically the boundary of that strip, if we could measure this for all times, we could reconstruct certain things or something like this, or.
I guess, but also I wonder if you measure A of t b for some finite number of times,
yeah,
and you measure b a t also for some finite number of times, but not necessarily at the same time. Indeed, in general, always they will be at different times, since. So if you're in that case, I wonder how I mean, it seems like there might be multiple betas that would be compatible with almost any given pairs of such sets of finite sets of measurements, because you could continue in different ways. You could continue to a continuous function for the AT-B case and for the BAT cases. Arbitrarily, after all, I mean, you can. There's an infinite number of continuous functions that will fit any finite set of data.
Yeah, so you're saying instead of, okay, this should fit there, but I could also go like this, yeah? And it's still fine. I'm still interpolating.
Right.
Yeah, but I personally think this degeneracy is not exactly how we do physics, right? For example, let me reverse the logic and say that Alice and Bob prepares a state in such a way that locally in their own lab is a vacuum state. But because they are space-like, between their labs, it could be some crazy state. Does it make sense? So if you imagine Alice and Bob, and then there's a Charlie in between, Charlie might prepare an extremely excited state, but Bob and Alice still sees the vacuum state. All that means is that from the perspective of quantum field theory, which is actually true just from quantum field theory, the mathematical theory of quantum field theory, local vacuum has infinitely many degeneracies, right? You can always stitch in between them to get any arbitrary state. There's not a vacuum state. But you see here, the logic is the other way around. I'm telling you that I'm doing an experiment where I take my global system to be in a vacuum state and I ask what a local algebra does. So you are not assuming infinitely many possibilities to fit this stuff because you are not trying to ask for how many results are consistent with this, right? But I guess you're right that, you know, like the problem with doing with systems with infinite degrees of freedom is that in principle, there's always a way to wiggle things out. And now the question is, when you set up such an experiment, you do what you think was the natural fit, I guess, right? If I want to do a thermodynamics experiment, I shouldn't consider singular cases where this thing there's some stuff that complete, like the 2-point functions are thermal with respect to Alice and Bob, and then if I put a Charlie, then it doesn't see thermality. And when that happens, again, I would say that, you know, as an experimentalist and a theorist, you should ask yourself, like, under what circumstances you expect this, like, diverging behavior from the expected thermality. I guess it all depends on how you do the experiment, and I'm not familiar with how real experiments on this kind of thermal states associated to local observers are done. So I'll leave it at that, actually.
Anyway, thanks, Erickson. This for me was very helpful indeed. You present these things really nicely. Thank you.
Thank you.
Yeah, thank you very much, Erickson. I think we will close the recording here and maybe still discuss if somebody wants to discuss. But fantastic series. Thank you very much. That was
no problem.
That's really very.
Okay. Should I shut down the sharing screen?
Okay, I finished the recording. Thank you, Erickson. And okay, thank you very much.